Hello, and once again, welcome to the 12th class. Is it the 12th class today? 12th class on coordination chemistry. And good morning, everyone who are here with me in Zoom, like Amlan, RS, and Udit, and many will join. And those who will be joining in the YouTube soon. Today, we are going to have a very fascinating discussion on color properties. Let me share my screen where I will stop the annotation from your side. And Chris is now on the, well, yes, yesterday we had seen that the color, uh, in general, color of a compound, particularly the inorganic compound, mostly transition metal compounds, and most specifically transition metal complexes, they have color properties. Some of them are colorless for some reasons, but many of them are colored. And the color property is due to two possible transitions. One is the DD transition, which is most common and most simple, but this CTS is the most dominant. Let me tell you that the intensity of absorption peak is very high for CTS. I will tell you what is CTS very soon, but just I am sounding you that a symbol called epsilon, that is called the absorptivity, which will give you the relative intensity, is quite high, 100 to 10 to the power 6. While DD transition is very, very weak, intense color. Since since the absorption has high intensity, the color is also intense color. If you find something intense color like permanganate is a permanganate ion is purple, it's intense purple. So that cannot be due to DD transition. It is, of course, you might not know from a very look whether it is an intense color or a light color, that you have to go to a colorimeter and take the spectrum and see how intense it is. And this is a weak epsilon, lies between 0 to max say 10, 20. Weak absorption, and hence light colors. All the colors are light. And for you, for your examination purpose, DD transition is important for your board. But in in competitive tests, CTS comes in a very big way, because most of the colors are not due to DD transition, but due to CTS. So we have to know everything in details. The simplest among them is DD transition for octahedral complex. One electron from the lower set, the T2G set, will transit, be excited to a vacant place not orbital, place. Even if it is D9, then it can get a place so that it will absorb certain radiation. And that absorption is not a monochromatic absorption, it is polychromatic, because each electronic transition is associated with some vibrational level transition. Each electronic level has some vibrational level, and each vibrational level has some rotational levels. So there are several combinations of the electron transiting from a lower energy state of say T2Z to EZ. So therefore, always the absorption peak, electronic absorption peak in the UV visible region comes as a mountain with some maximum point we call lambda max, giving the maximum intensity at that intermediate region. And in fact, uh, the DT transitions that we have seen, they are forbidden transitions actually. That is why, so when we say forbidden transition, don't be swayed away with the literary meaning of the term forbidden. You are forbidden to drink alcohol. That means you will not drink alcohol. But in chemistry, forbiddenness means the allowedness is very less. The probability of transition is less. So it will give, and I will tell you that the allowedness, the forbiddenness rather, is somehow partially allowed due to the breakdown of the selection rule. For some bad reasons, there is a partial breakdown of the selection rules for which the DD transition is partially allowed, out of which the tetrahedral DD transition is more partially allowed than the DD transition for octahedral complex. I will tell you uh, because because any transition which involves a change of azimuthal quantum number delta L plus minus 1, like P to D or D to P, S to P or P to S, plus minus 1, that is allowed. That is called Laporte allowed transition. Selection rule, quantum mechanically it has been established that when delta L is plus minus 1, then it is an allowed transition. And if it is allowed, the intensity of absorption will be high. The mountain will be very, Kilimanjaro type or Himalayan type. And therefore, the intensity of absorption, if the absorption is of high intensity, then the complementary color that we see is also of high intensity. And we get intense color. But del L, change in L is 0, like D to D, P to P, that transition is Laporte forbidden. But, this rule is applicable strictly when there is a G-Gerard symmetry, point of symmetry or inversion center. Since tetrahedral geometry has no Gerard symmetry, no inversion center, so this rule is partially broken down, partially broken down. And that also, there is another rule called spin allowedness. If this delta S is equal to 0, then it is allowed. That means if from the T2G set, an electron is spinning, say anticlockwise, it will go as such. For example, when you go for a HS complex, hund, then it goes in the same direction. So when a T2G electron will go, it will go the one, supposing there is no paired electron. Had there been a paired electron, 4 electron there, at least D6, and it is high spin. Hound, poly. Then that one, which is spinning anticlockwise, then that will be transiting to the higher energy level. You know, DD transition will be, although Laporte forbidden, but there is a breakdown of partial breakdown of this rule for which it is slightly allowed, but then only it has to be spin allowed. If it will be spin disallowed, then the intensity is still less. In most of the tetrahedral and HS complexes, uh, spin allowedness is there. So if one of them is in the anticlockwise here, it will go straight to anticlockwise to pair the other one. But if all are in same direction and this will go, that will be spin forbidden. It has to flip. Flipping means del S is not equal to 0. So that is spin wise, it is forbidden. L wise, del L should be plus minus 1. Spin wise, del S should be 0. Any change will be disallowed. But I am reminded of that, astrologers, they say that your Ketu is sitting on your head, so it will be creating a lot of havoc, and you will not succeed in your examination, or you will be having this poor health for a longer time. But if you wear a tabiz or a ring with some pearl, which will be given by him, he will be arranging that 24 karat pearl or gemstone, and will calculate according to uh, your stars, planets, and all that. Then only this Rahu's effect will be reduced. It will not be totally vanished, reduced. So you would have been a first, would have got in NEET in AIMS Delhi. You will get AIMS maybe Bhubaneswar, or AIMS maybe Jipmar, or SCB Medical. So situation, I'm just kidding that the breakdown of selection rule happens due to some reasons. I'll tell you, for which the DD transition is partially allowed, but if this Laporte forbiddenness is partially allowed, if spin forbiddenness is there, in most octahedral complexes, the spin forbiddenness is there, you will find the intensity is the least. Square planar complex and octahedral, they are brothers. Square planar complex is nothing but an extreme case of tetragonally distorted octahedron, where the transligands are completely withdrawn and pocketed. So guys, we are joined by Nihar uh, and Sai. Uditma is there, Riddhi, Siddhi, Krishna. Very good. So yesterday we had a color wheel. We started from 400, then the uh, jumps, the gaps has to be remembered: 30, 60, 70. Then what? 30, 30, 60, 70, then 20, then 70 again, then 100. So you'll go from 400 to 700 in anti-clockwise manner. You just ignore indigo, VBGYOR. So if a certain complex having higher delta 0, a strong field ligand that will absorb in this VBB region, it will look YOR. But those whose delo is less, they will absorb in the ROY region, and they will be looking GBB. B. So with this, we went yesterday and D0 and D10 complexes, they do not have a possibility of DD transition. So they are usually colorless, but CTS will come into picture where even D0 can be colored, D10 can be colored. So DD transition will indicate that it is colorless. And sometimes if the entire absorption peak falls in the UV region, then I think I have written or not. The entire, have we written somewhere? Yes. Have you written? No. Have you written? Yes or
Yes,
no?
sir. Written. Yes, sir.
If the entire absorption peak falls in the UV region, where? I don't
Sir,
get it.
intensity of color just ಪೂರ್ವರು data points ಪೂರ್ವರು. Yes, sir. If the
Oh,
complex.
yeah. Thank you, Dit. Well, yes. So today we shall be taking up this. We have not yet. I am every time I am trying to revise. I'm making up my mind to spend some time for revision. So I'm not able to do that because the program is going very deep rooted. That is why. Now I have some question for you. We shall be doing that. I will send you today. I have added so many things. This is the color wheel. And also, yes, yes. Let us solve this problem. Uh, see, are you able to see my screen?
Yes, sir.
Yes, sir.
Yes, sir.
An octahedral complex has lambda x is 535 nanometer. Now tell me in which region does it fall? Look to your color wheel. 535 nanometer falls in which region?
Green.
Green.
So what color it will exhibit? What will be the color that we
Red.
see?
Red.
Red.
What? Tell me. What?
Red.
Red.
Red. Therefore, you are asked to find if del O, find del O and which color it will exhibit. 535 nanometer is itself green. It is absorption. If it absorbs the green color light, then it will appear red. And that absorption lambda max is to be taken to find del O, because that is given in angstrom unit. I mean, sorry, in wavelength, in terms of wavelength. Usually that is given in terms of nu bar, wave number. But here it is given in, because color wheel has to be compared. So in lambda, in terms of lambda. And we converted this with same SI unit. We found that del O is this 3.78 10 to the minus 19 joule. Some of the complexes due to DD transition, you find this is D2 vanadium, hexaqua vanadium. 3 plus is D2 configuration green, and it is D3 configuration vanadium 2 plus is purple. But if it is plus 5, it will be colorless. But vanadium pentoxide is not colorless. I will tell you that many compounds which are D0, they can be intensely colored due to CTS. Out of cobalt 3 plus complexes with chloride ion and ammonia ligands, one appears orange and one appears blue. Predict which is which. So supposing you have hexa amine cobalt 3 plus and COCl6 3 minus. Out of this, one is orange, the other is blue. You have to identify which is which. I told you, anyone? Welcome those who are watching, have started watching from the YouTube. Good morning. And you can wish me good morning in the chat box. So we are stretching the color properties today to a great extent. We'll be doing. So tell me.
So first set a blue above. Second
Now,
SCOC. Uh,
Udit says the first one, the amine complex will be blue and the chlorido complex will be orange. Anybody who agrees with Udit? Anyone? Krishna, you agree?
Yes, sir.
Well, amine is a strong field ligand compared to chlorido. So this delta 0 for this complex, supposing this is complex 1 and this is complex 2. So delta 0 for complex 1 is greater than delta 0 for complex 2. So this will absorb the lambda max of complex 1 should be less than lambda max of complex 2 because energy is inversely proportional to wavelength. So this has to absorb at a lower wavelength, that is in the VBG region, and it will look YOR. So if you draw immediately, horizontal line and have a practice starting from 400, this is 4, how much?
30,
30, then 4,
90,
90.
then 500, 60,
60,
then 20, 580, then again 70. How much?
650.
Then
750.
100. So this will be 750. So since amine is a relatively stronger ligand, it will be, this is V, B, G. These are the stronger field ligands. They absorb and they emit the complementary color. B, Y, O, R. The indigo is deleted. So the color out of the two colors, one is blue, the other one is orange. So definitely this amine complex will be absorbing from these three: violet, blue, green region. We do not know. It will be appearing, or the complementary color will have greater wavelength. So since orange is one of them from the YOR region and blue is in the VBG region, so definitely this will be absorbing in the blue region. Indirectly we know, and it will appear orange. So what you answered is found to be incorrect because lambda max is lower for this. VBG, their lower lambda. Lambda, this is del O is greater means the lambda is smaller. Lambda smaller means they will absorb at a VBG region. So the complementary color that we will observe. So orange is from the upper region, from the YOR region, and VBG region is the blue that is here. So did you get your mistake, Miss Master Udit?
Yes, sir.
So what color hexamine cobalt will exhibit?
Orange.
अरे what color it will exhibit? Sorry sir, कहने से क्या फायदा?
Orange.
So since it will absorb in the blue region, it will appear orange. So just the opposite. Obviously, say chlorido is a weak field ligand, lambda more, it will absorb in the orange region, just the opposite, and appear blue. So this is a blue complex. So let me control V. I I deleted the answer by making control X. Let me show you what I have written. And appears blue. So chlorido ligand will appear blue and amine ligand will appear orange. Got it?
Yes,
Yes,
sir.
sir.
So I think
Yes,
I
sir.
will drop the answer in a another solution will be there, and here the explanation let it be there. Now this I am taking to the other one. You do it. Supposing you are given the absorption maximum of few complexes are given. These are normal complexes where CTS will not come. Of course, uh, CTS will come in pi acceptor ligands like cyanide, but it is clearly given. Doesn't matter whether it is CTS or DD. When you are given the lambda max, you can calculate the complementary color and predict the color. You may not say whether it is due to DD. Most of them are DD, but many of them are dominated by CTS. Today I shall be explaining you in details what is CTS, Charge Transfer Spectra. Now tell me, C to the color wheel. Tetrafluorido cobalt fluorido is a weak field ligand, so it is absorbing at a lower energy, higher wavelength. So what is 700 falls in which region? Again we draw cross and horizontal line. 400, 430, 490, 400. Oh, sorry. Ah, 560, 580, then 650, then 750. VBGYOR. So 700 falls in which region?
Red.
Red,
So how do you look?
green,
Ares, if it is
Green.
absorbing red, then the complementary color will be observed by us. So write down green. This color is green. Then what about pentamine chlorido cobalt 3?
Red.
535. 535 falls in the green region. So it will appear what?
Red.
red,
So it
Red.
red. Then hexa aqua cobalt 3 plus, it is a uh, low spin complex because cobalt 3 plus is a hero marca teacher. Aqua is a intermediate field ligand, although commonly it is the weak field ligand, but 3 plus will make it a, a low spin complex. All the 6 electrons will be all remaining in the T2G set, but 1 electron can jump without change of spin. No harm. There is vacancy. There is no harm. So it is Delo is little bit larger because water is there. So not as large as lambda is not as large as chlorido, but 600. So 600 falls in which region?
Orange.
orange,
Orange.
So how does it look? The complex
blue,
Blue.
blue, it will be blue. So what about hexamine cobalt 3 plus? A hero marca. This is hero marca. Amine ligand is stronger than aqua. So the energy is more, lambda is less, 475. 475
orange,
falls in which region?
Blue.
Blue.
So
Blue.
it will look what?
Orange.
Orange. Then this is Hiromarka. Cyanidoligands, they are very strong field ligand. And let me tell you that the actual cause of the color, if at all there is a color, it is due to CTS. Because the DD transition peak is buried inside a very intense CTS peak. So anyway, it is given 310 nanometer, which is in the UV region, but the tail is extending to the violet region. So if tail, some part is there in the violet region, what is the complementary color of violet?
Light
Yellow.
yellow. Yellow.
What,
Yellow.
what? Kaun kohila Amlan? What did you say, Amlan?
Light yellow.
Yes, precisely light. Because a little bit, supposing this is the visible region from 400 to 800 nanometer, and this is the UV region. So the big mountain is here, and it is slightly protruding or extending to the violet region. So that it will be the complementary color will be yellow, and that will be light yellow because the intensity is very less of the violet. So most of the cyanide complexes are colorless because many of them remain, the mountain remains in the UV region, but a few of them are light yellow because the a very small part of the mountain peak, I mean the absorption peak, extends to the violet region. So it is light yellow. And the DD transition peak somewhere is buried inside. That also Delo is high, that falls in the UV region, but that is buried inside. So we find the color, if at all there is a color, some carbonyl complexes, chromium hexacarbonyl. This complex is light yellow. Same thing, it is not due to DD transition, it is due to the charge transition. I'll tell you in details. There is two types of, in fact, four types of CTS. So out of them, two are very common. So this is the LMCT, MLCT, both, mostly MLCT, also LMCT. I will tell you what. So you will do it, these things are at home. Uh, Another question is there. Certain complex has a Delo in the unit of joule. What color it will exhibit? You find lambda is this. Convert it to nanometer. This will come in meter. So convert 10 to the power minus 9, make it meter. 530, and look to your color wheel. Always practice the color wheel. 530 falls in the green region. So what color it will exhibit?
Red.
Red. So this will appear red. So you have to do all these things. Then we enter into CTS. After CTS, we will revise. Now see, many D0 metal ions, for example, permanganate is purple. Chromate is yellow. Dichromate is orange. Of course, this will be, it will be deceiving you. This is a tetrahedral tetrachloride or nickelate. It will look like as a DD transition, but the most intense color is the green color is due to the CTS. So DD transition is one, and how will you know that the color is due to DD transition or CTS? First of all, whether the color is light or maybe yellow, maybe blue, it should be light. If it is very intense blue, intense purple, intense green, then it could be mostly due to CTS. In CTS, what happens? One electron from the ligand sigma bonding orbital or a pi bonding orbital, if it has a pi bond, one electron is excited to the vacant orbital T2G or EG, whichever is vacant. And during this transition, it will absorb, same principle, it will absorb some energy. If it falls in the visible region, then the complementary color will also visible. In this permanganate, dichromate, chromate, their intense peak, it is a P to D transition. Del L is equal to 1. So it is highly allowed, Laporte allowed, because the ligand has the lone pair orbital uh, in the p orbital, mostly in the p orbital, the field orbital. Well, we call it sigma orbital because it is a hybrid orbital. It is there in the hybrid orbital, so it is there. So, of course, it is a lone pair orbital. We call it a sigma orbital. So, one electron from there, p, goes to d, either T2G, whichever is vacant. If T2G is completely filled, then the higher energy. If there is a vacancy in T2G, lower energy, then it will prefer the lower energy because stability is the requirement for everyone. So this transition will not only be Laporte allowed, but also spin allowed. It will pair. So it is so intense that the epsilon, which is a measure of the absorption, that is itself called absorptivity, is more than 1000, some 10 to the 3, 10 to the 6. So it is strong, a very intense signal. And the color is equally intense. And the other one is, this is called LMCT, ligand to metal charge transfer. Charge means electron. The other way is possible. One electron from the ligand, either EG or T2G, whichever is available, is excited or is transited to one of the vacant, usually antibonding orbital of the ligand. That happens only when there is a pi bond. Pi acceptor ligands like cyanide, like pyridine, like phenanthroline, like nitrito, and like these things. Carbonyl. So they have a pi bond, they have an antibonding orbital pi star. So that will receive the electron from T2G or EG set will come. During that, it will absorb radiation and that will give absorption peak, and we predict the color as its complementary color that we see. And most of the, barring a few like permanganate, dichromate, chromate, and all, many, majority of them, particularly with pi acceptor ligands, the energy of transition is so high, the CTS energy is so high that lambda falls exclusively, mostly in the UV region. And sometimes the tail extends to the visible region. Therefore, many of the carbonyl complexes are light yellow colored. Otherwise, they are colorless. Cyanide complexes are colorless because the most important transition is CTS. I will tell you one by one that this I have already told you there are, in fact, 4 types of CTS. Charge transfer. DD is within the transition metal, the splitting T2G to EG or EG to T2G if it is tetrahedral. So that is internal, I mean inside the metal ion. But if the electron is being excited from the ligand to metal ion or metal ion to ligand, or between metal ion to metal ion. If there are two metal ions, one is outside the coordination sphere, the other one is inside the coordination sphere, and electron is being exchanged, then that is called MMCT, metal to metal charge transfer. Sometimes it is called intervalence charge transfer. Sometimes ligand to ligand. Metal ion will remain as a spectator, but there are 2 types of ligands. One is a donor ligand, one is an acceptor ligand. So there will be a transition from this to this. via the metal ion, it will transit and it will absorb some color and the complementary color we see. Now, LMCT, I have already told you sigma or pi electron from the ligand will be transited to one of the empty d orbitals, Eg or T2g. Uh, and that happens, most importantly, that happens when the oxidation state of the metal ion is very high. If there is no d electron or at least one electron, few d electrons, oxidation state should be very high so that it will have a strong tendency to attract electron from the ligand. So that is the symptom, that whether it is LMCT or MLCT. So ligand to metal, LMCT, V plus 5, Mn plus 7, chromium plus 6, titanium plus 4, they have all D0 configuration. They are suitable for the LMCT. And those which are pi donor ligands, I was telling about pi acceptor ligands like cyanide, like carbon monoxide, nitrite N, and so on. But chloride, bromide, iodide, oxide, sulfide, these are pi donors. They have lone pairs. They can form pi bond. That we shall study in MO theory in a separate class. MOT, that is ligand field theory. I will be taking classes because I have been making this irrespective of whether people are watching later or people are not much interested in a higher level thinking. Doesn't matter. If one of you, Chris and Amlan or others, RS, they are interested, then and others who are watching, I am looking to my analytics that yes, a few guys are watching. A long time they are watching means, because analytics will tell you how many of the viewers have spent how long in that video. That will tell you that some are just living within 1 minute, 2 minutes, 3 minutes average, how much, and individually also they will give you the data. So that's it. That's it. I do not have any any much desire that I should be accessible to uh, thousands and thousands, because I'm so experienced. My video should be watched by one and all. I don't say that. So these pi donor ligands is one condition, and the oxidation state should be very, very high. Either it will be totally D0 or maybe one electron, two electron in the D. That will be a suitable candidate for receiving electron. And if the pi donor ligands like chloride, bromide, iodide, oxide, sulfide, they will be giving, because they have a lone pair in the sigma uh, orbital, and they will be giving. It's non-bonding orbital, of course. They will be donating. One electron will be enough. Now see, permanganate is purple, chromate is yellow, dichromate is orange, vanadate is yellow, vanadil VO2 plus is yellow because this is plus 5. And this is slightly changed. This is plus 4 is, pale blue. These have D0 configuration. The DD transition is not possible at all, but they are intensely colored because one of the electrons from oxide, here in all the cases oxide, is being promoted to one of the vacant orbitals of E2G or EG in the metal ion. And CDS, even they do not look like a complex. It is a binary compound like CDS. It is yellow. It is all due to CTS. And sulfido is a pi donor ligand, and therefore cadmium 2 plus, it is oxidation state is plus 2. But since it is a pi donor ligand, sulfido, so it is a LMCT complex, and that is yellow. Yellow is we are looking means you can find out what color it must be absorbing to the color wheel we have been doing time and again the CDS must be absorbing. If it is looking yellow, then it will be absorbing in the violet region. So I will be giving you a brief note. First, let me finish. Titanium tetrabromide, titanium tetrachloride, it is colorless. Chlorido ligand is not able to, but bromido and iodido, that is a very good donor. It has got a strong tendency to be reduced, to be oxidized. They are good reducing agents. Iodide is the best reducing agent, as you know. So they give. Titanium is D0 configuration. फिर भी titanium tetrabromide is orange, titanium iodide, tetraiodide is violet. And I am showing you the spectrum, the absorption spectrum of permanganate ion, which lambda max falls in the vicinity of 530 to 570, and therefore it absorbs in the GY region and hence appear purple. Everything has a logic. So all this will be colored due to CTS. And what CTS? MLCTS. MLCT. Now I have given all these LMCT, cuprous oxide is red, even if it doesn't look like a complex, but still it is a transition metal compound. It is D10 configuration. All are D10. Sorry, D0 configuration, excepting ferric oxide, vanadium pentoxide, vanadium is D0. Stannous tetraiodide is, stannous plus 4 state. There is no uh, p electron, no s electron. The 5p0, 4p0. So the plus 4 state, highly oxidized state is stannous. Although it is not a transition metal ion, iodide ion is a very strong pi donor ligand, and therefore there is a CTS, LMCTS. CuI is brown, cuprous oxide is red, silver iodide is yellow, mercury iodide is red. And the transitions I have written from the pi orbital of the ligand. From the pi means it is what pi, what I say pi is the pi bonding in the concept of the ligand field theory. I am saying they are already engaged in pi bonding, so that we do not know unless we know about ligand field theory. We do not know how the non-bonding electron that we say that engaged in really pi bonding with the metal ion, that will be only known. That is why I am using the term pi sigma, not non-bonding here, because they are engaged. Are you engaged? Are you seeing someone? Oh, I'm sorry. This is live recording. I'm sorry. Hello and welcome. So the vacant orbital here is 5s, and I have written which vacant orbital it will go. Not necessarily it will be is cadmium, uh, is a fake transition metal. Zinc, cadmium, mercury doesn't have a vacant D, so it has to go to 5s. So others to D. Similarly, and all these things you will find. Here I have given you together. If it is LMCT, you find an electron from the ligands will be transited to either EG or T2G, usually sigma, in some cases pi. In many cases pi, particularly pi donor ligands like chlorido, bromido, iodido, it goes from the pi. They are pi donor ligands, so they require less energy for the promotion to EG or T2G. But the other way around is MLCT that we shall study. So it will go from either T2G or EG. That electron will go to a vacant antibonding orbital of the ligand, and that needs a pi bond, and that is why I call a pi acceptor ligand is necessary for MLCT type of uh, spectra. Now here LMCT is strong, intense. I am showing you how most of the LMCT comes in the ultraviolet region. I'm not talking of permanganate, vanadil, chromate, dichromate. They fall in this region. Otherwise, they cannot be intensely colored. Here I have taken a cyanide or carbonyl complex where the LMCT big the Kilimanjaro mountain falls below 400, and sometimes the tail comes to here it doesn't come. And here there is a DD transition, so some light color will be found. I'm showing two DD transitions just for fun. Just for fun. There will be one DD transition. I'm showing two DD transition just for fun. So if it falls in this 400 to 800 region, then it will be colored, lightly colored eddy transition. But LMCT also can fall inside the 400 to 600 if it is LMCT. But mostly MLCT, they have large, DELO. I mean, so that's not called DELO. That is called CTS energy is large. So almost all of them fall in the UV region. Now coming to the factors involving LMCT, uh, this is for fun. It's not really important for you. The LMCT energy is dependent on size of the ligand. This is chloride taking more energy, that falls in the ultraviolet region. But bromido, iodido, I was talking about titanium, tetra, bromide and tetraiodido. They are colored because their energy, LMCT energy is less, that falls in the visible region. So size, if size is more, then the LMCT energy is less, and therefore you may expect in the visible region. And oxidation state, more is the oxidation state, less is the energy you are likely to find in the visible region. Rhodium 2, rhodium 4. And also across a D series, if the size is slightly decreasing, that is D block contraction, and you find there is a decrease in the LMCT energy. So that maybe some vanadium, even if all of them fall in the visible region, you can expect that vanadium complexes of particular same oxidation state with same ligands will require more energy. Lambda may fall in the VBG region, and we see the YOR. But in the other cases, slowly they will be falling in the other region, and we may get this color. For example, permanganate. Permanganate is looking purple. Purple is close to violet. Violet. We treat purple as violet because it is absorbing in the other region, orange region, right? What is the complementary color of violet?
Yellow.
Yellow region, and hence it is absorbing it is showing, it is exhibiting the violet or purple color. So these are some minor details which will not be at all required for you unless you are a mad fellow like some of you. I will not name. Down the group, in any transition group, as you go down a group, it will require more and more energy. So the likelihood of falling in the UV region will be more. But the 3D series, the likelihood of falling in the visible region is more, because the energy is less, means the lambda is more, and so on. Even all of them can fall in the visible region depending on the ligand, but you can differentiate between them whose DELO is more. I mean, not DELO is city energy is more, and accordingly you can predict which region it will absorb and what will be its emitted color or transmitted color. So these things I have written. And then we talk about ML spectra. This is metal to ligand, and that has two requirements. One, the oxidation state should be low. They are high. The number of d electrons should be at least 0, the minimum 0, or maybe 1, 2, like that. High oxidation state, but here the oxidation state should be low. It should lose either no electron, like the carbonyl complex of chromium, molybdenum, iron, which are neutral complexes, or small, so that it will have enough electron which are undergoing a lot of repulsion in the d, and it will be interested to be donated to some vacant higher energy orbital of the ligand, the antibonding orbital of the ligand. So that is one. A complex in which metal has lower oxidation state has many d electrons and thus have greater energy to donate it to a low-lying pi star orbital of the ligand. So ligand should be pi acceptor, so that it should have a antibonding higher energy, but low lying, so that it will, it will fall, it will go from the T2G or Eg of the metal ion to the pi star easily. Low lying matlab it's not that it is lower than this. It will be low lying. It's not a pi star high energy, but low lying means it will be, the difference will be small, so that the energy required should be falling in the visible region, so that we can expect a color. So, but the difference is really large. Carbon monoxide, cyanide, nitritos, thiocyanato, nitrocilium, this is NO is a neutral, is nitrosyl, it is NO plus, nitrocilium, bipyridine, phenanthrolene, pyridine. These have pi bonds and they have pi star orbitals, antibonding vacant orbitals. They will go for MLCT. Even Cu plus 1 having D10 configuration, you expect, I told you an example that CuCN whole 3, CuCN whole 4 3 minus, where Cu is in the plus 1 state is D10 because there is no DD transition. Therefore, it is colorless. So that is just for sake of beginner. But such complexes, they show intense MLCT, MLCT peak in the UV region, but that doesn't extend to the visible region. Therefore, we say colorless, and we sometimes write there is no D10, so no DD transition. Yes, there is no DD transition, but still that can be color if there is an extension of the intense UV, peak in the UV region towards the violet region. Now I will show you many examples where copper plus 1, they are colored with pi acceptor ligands. Some complexes with pi acceptor ligands like carbon monoxide, they are very intriguing. They can accept electron and they can also have a donation. So they form both LMCT and MLCT, but the probability of MLCT is more. So it is very difficult to distinguish whether the spectrum is due to MLCT or LMCT. Although the probability of MLCT is more, because the ligands like CO, triple bond O and all that, they are chromophores. They themselves can absorb. Therefore, one electron from them, from the bonding orbital, I'm not talking of antibonding is vacant, can be, can be transited to a vacant d orbital, D2G or EG orbital. So both LMCT and CTML, MLCT and MLCT and LMCT, MLCT and LMCT are possible for them. Most complex, such complexes are colorless because absorption peaks falls entirely in the UV region. But in some of them, like hexacarbonyl chromium 0, is light yellow, and most of the cyanide complexes are colorless, but some of them are light yellow because the MLCT or both, they are all huge peak. That could be both due to MLCT and LMCT, and that if it is protruding towards the violet region, then it looks yellow. The DD transition for them mostly buried inside the strong CTS peak, because their delo is also cyanide, carbonyl, their delo is large. Even DD transition also falls in the UV region, but that is not seen. It is buried. The example for this phenanthrolene copper 1. This is a copper 1, D10 configuration copper 1 is dark orange. It is a tetrahedral complex, dark orange D10. This is not due to DD, it is due to CTS and mostly due to MLCT because there is a pi bond. So you may not say LMCT, but you definitely will say MLCT because the metal will have an electron in T2G or EG, which will give to the vacant antibonding orbital of the pi acceptor ligand. So MLCT is a must. LMCT you may not say, but in practice both are possible. Now this blood red color ferric thiocyanate, actually we say a double displacement reaction ferric thiocyanate is blood red, but actually there are several complexes. It is a complex. Mono, that is only thiocyanato ferret 3, bis thiocyanato ferret 3. This is tris thiocyanato ferret 3. All three. This is tetrakis thiocyanato ferret. This is iron. I'm sorry. This is iron 3. Iron 3. This is iron 3 because it's a neutral complex. But here it will be ferret. Tetrathiocyanato ferret 3. This will be thiocyanato iron 2. Iron 3. Iron 3. Dicyanito iron 3. All iron 3. These are colored due to LMCT because sulfur is a pi donor ligand, LMCT. But since it has a pi acceptor property, so you cannot ignore that MLCT is not possible because there is a pi bond here in the structure of SCN. So LMCT and MLCT and LMCT goes together for such pi acceptor ligands, not for chlorido, bromido, oxido. The possibility of MLCT doesn't arise. LM, not ML. Because they do not have an antibonding orbital. Well, manganese 2 plus is pale pink and manganese dioxide is black is due to what? Is due to DD transition. Here, Mn2 plus is D5 configuration. So there is aqua complex. In water is nothing is there, aqua is there. So there the peak has been found to be less intense and therefore it cannot be due to the CTS. It is due to DD. And this black, that means it is not, it is absorbing all. So that also is due to DD transition. You must remember. But Mn plus 6 green, Mn plus 7 purple permanganate, these are due to CTS. Then these are very rare cases that metal to metal CT, MMCT, IVCT. For example, Prussian blue. Sometimes we write Fe4 FeCN whole 6 whole 3. Actually, it is KFe FeCN whole 6. Inside is ferrous, outside is ferric. That is called Prussian blue. But it will be ferrous ferricyanide. This is called Turnbull's blue. Both are blue, but the color is due to the electron, one of the electron coming from ferrous to ferric. In here, inside the coordination sphere to outside, but in here, outside the coordination sphere to inside. So this is called intervalence charge transfer spectra. No DD transition, nothing in ferrocyanide ion. Cyanide ion is giving an CTS. In such a CTS which is falling, it is giving CTS. Multiple spectra are there. In cyanide complexes, undoubtedly CTS is there in this ML CTS, LM CTS are there in the UV region. But the color that we see, Prussian blue, they are not due to LM CTS, it is due to MM CTS or IBCT. That is the metal to metal charge transfer. That falls in the visible region, right? Similarly, the red lead, which is red in color. Fortunately, we have studied by mistake, before Udit could indicate Vidyut could indicate that solid state has been abolished from plus 2 from CBSE and hence plus 2. We had already covered PB304 has a spinal structure. That is PBO. This is uh, uh, it's not it's not spinal structure. It is I'm so sorry. Spinal structure, one will be plus 2, the other one is plus 3. But PB304 is plus 2 and the other one is plus 4. So by mistake I have written. So PB304 is read due to electron transfer from PB plus 2 plus 4. This is also a case of MMCT. Similarly, ferrospheric oxide or magnetic oxide is inverse spinal. That the reddish brown color is due to the electron transition from ferrous to ferric. These are the examples of MMCT. But there are very few cases where there is LLCT. This is hi-fi case where some very complicated complexes involving the ligand belonging to a donor type, another ligand belonging to the acceptor type, like a Reba complex. Reba is rhenium plus 1 complex using a very unusual ligand DCEB, which is 4,4-bis ethoxycarbonyl 2,2-bipyridine. And the other one is 3D MABN, that is 3-dimethyl-amino-benzonitrile. So this 3DM ABN is electron donor and this DCBE is electron acceptor. So the electron transfer occurs within the ligands without involving the metal ion. So this is LLCT. So I have already told you that absorbance, the forbiddenness, allowedness is governed by two rules. One is Laporte selection rule, that del L, if it is plus minus 1, P to D, S to P, they are allowed, but P to P, D to D, they are forbidden because they lack. And this rule is strictly applicable for those having G symmetry, octahedral field or square planar. Octahedral and square planar, they have a G symmetry if all the ligands are same, talking of that. And tetrahedral, they lack G symmetry, so that is a slight violation of the Laporte selection rule. So it is slightly allowed, the Laporte allowed transition for TD. Now the selection rule for the spin, delta S should be 0. Whatever spin was there in the lower set, same will be retained in the higher state. Otherwise, the flipping is forbidden. But some breakdown happens of the selection rule, particularly the Laporte selection rule, is due to vibronic. Vibronic coupling means, you know, the bonds, they vibrate. If a common atom is there, there are two bonds, then there can be two modes of vibration. If both bonds are, vibrating in the same phase, both are expanding, both are contracting. This is called symmetric vibration. And if one is contracting, the other one is in expanding, then that is called asymmetric stretching vibration. Then in that case, it lacks a center of symmetry. Even if it is octahedral, one is in this state, the other one is at this state, at that time, the inversion center is missing. So that is a partial breakdown of the selection rule. And in complexes, there is a huge dp mixing, d orbital, p orbital, they mix. So therefore, d to p is allowed, but d to d is disallowed. You cannot say because d is mixed with p, some p is mixed with d. So it is partially allowed. Spin orbit coupling, spin is not the only factor giving magnetic moment. The orbital motion is also having spin. So there is always a vector sum of this spin produced by magnetic moment produced by the spinning electron and orbital motion. That is called LS coupling. So that makes the spin selection rule little relaxed. So you cannot say that del S will be 0. So same spin will be retained, inversion is possible. So due to the partial breakdown of the selection rules, The DD transition, which is Laporte forbidden, it is partially allowed and but partially allowed. So the absorption is little less. Epsilon, if it is, so tetrahedral complexes, they are spin allowed. If the spin allowed, it will be say 2 to 10. If it is spin disallowed, Laporte forbidden is the inherent nature, but tetrahedral partially Laporte allowed because it is not having a G symmetry. And also if there is a spin allowedness, then the tetrahedral, I have written down here CTS. I have also written in the last note that CTS spectra is most intense, followed by TD, and the most, the little, the lightest color is that of octahedral or square planar. Now, I have given you an example. Hexaqua cobalt 2 complex is HS complex because cobalt 2 plus is a very poor feature metal ion and aqua is an intermediate field ligand. So this is a high speed complex. D7, hund, then poly. So poly. So there will be 3 unpaired electrons. So it's pale pink, but little more intense than previous complex, because here it was spin forbidden and here it is been allowed, because there was some poly is there, so that poly will go and pair without change in spin, so that is why it is spin allowed. Therefore its absorptivity is little more. Even if it is octahedral, the manganese 2 plus complex has a lower intensity, 0 to 0.1 epsilon. Both are HS complex, but it is a D5. Hund. So if one electron will go without change in spin, that will remain, two spin will be parallel, which is impossible. It has to revert its spin. So it is violating the, it will happen because, we have our astrologers. I'm kidding. Astrology is a science, is a pseudoscience or science. If there is Rahu or Ketu that is spoiling your life, then I will give you a tabiz, some gemstone which you wear, then the Ketu will have little effect. Similarly, there is a breakdown of the selection rule to some extent, so that even spin forbiddenness can have a little bit of, absorption, and hence some color will be found, although the intensity is very less. But tetrahedral complexes are little greater because they are slightly Laporte allowed. Here I have written this is, mm, you know, spin allowed and also slightly Laporte allowed, because is no strict Z symmetry is not there. Uh, so it's but this for manganate, dichromate, they are CTS. This is DD transition, but little, CTS. Now see, 1000 to 10 to the power 6. If you find in some question epsilon will be giving so high, then close your eyes and write it is CTS. And if it's so small peak, this 50 to 150 is TD, it is intermediate, because DD transition is partially allowed because it doesn't have a G symmetry, and if there is a spin allowedness is high spin complex, so spin allowedness will be there. So EG is below, so pairing is almost starting from even D6 में से शुरू हो जाता है, हुंड then poly. So so the spin allowedness is there for most of the metal ions, so it shows intermediate intensity. But the square planar and this octahedral, so the least intensity, out of which if it is spin allowed, it has got slightly greater intensity. So with this we complete today's session. How many of you are there? Udit is there. So when to write, or else you will write at home? I thought that I should give you a very simple note. So should I give now what we studied, or next time?
Sir, next time.
Okay, that will be on Monday. I mean your Tuesday morning, right? Because tomorrow I have a party.
Yes, sir.
I have a party to attend. Hats off to you, sir. Ritik Krishna is rating. Only I am watching Ritik Krishna. Thank you very much, Ritik. Ritwik Krishna. But I will give you the notes. But I have little time. I would have given you a very brief, concise notes on this. You writing, I dictating. But the extensive, files I'll be giving to you. But in the coming Tuesday morning class, I will first give you a write up, make a revision of what we did, then we go for stability of complexes. Bye bye. And if you have not yet, you feel like I'm begging. No, no, it's not begging. It's guys, you are just kids. This is the age of internet, and I hardly believe that I am an old man. I still feel that I am 16 years old. 16 years old man. 16 years old man. So I can work like what you are doing. So can you can subscribe to my channel if you have not yet. And why are you not hitting the like button? Is it so difficult to just hit a like button? Bye bye. See you on Tuesday morning, India. Bye.
Thank you, sir.
अरे रुह मो अरे केमती लागिला